Sí, sí se graba y sí se... Gracias. Ok, pues bueno, buenas tardes a todos. Bienvenidos al coloquio Arcadio Poveda de esta semana. Esta semana tenemos a un investigador que fue recientemente contratado aquí en el instituto y les voy a hacer una breve semblanza. El doctor Sierra Morales obtuvo el título de físico por la Universidad de San Carlos de Guatemala. Posteriormente realizó sus estudios de maestría y doctorado en astrofísica en el Instituto de Radioastronomía y Astrofísica de la UNAM en Morelia, enfocándose en el estudio de discos protoplanetarios bajo la asesoría de la doctora Susana Lizano, obteniendo la medalla Alfonso Caso en ambas. A partir del 2020 obtuvo 4 posiciones postdoctorales, 3 en Chile y otra más en la University College of London. A partir de noviembre del año pasado se incorporó a este instituto como investigador asociado y además a partir de enero está coorganizando el coloquio junto conmigo, entonces lo vamos a ver muy seguido. Y pues bueno, este coloquio se organizó para que pudiera presentarse y que toda la comunidad lo conozca. Entonces pues puedes comenzar.
Ok. Gracias, Mariana, por la introducción. Muy feliz de poder estar por acá. I will switch to English to present today's work. So my idea is to present this work that we published last year in 2 protoplanetary disks, where we are analyzing the dust trap properties of the disk around LkCa 15 and PDS 70. So and this is not working. Okay, so this is the table of contents. I will start explaining the physical processes taking place in protoplanetary disks that can explain what is a dust trap, right? So we are going to see a fast review of the dust trap mechanism. Then I want to do a fast review of how we model the millimeter wavelengths that we observe with telescopes like ALMA, for example. And then we are going to reveal the dust trap properties in LkCa 15 and PDS 70. These are the LkCa 15 disk and the PDS 70 disk. They are very famous. They have ring-like structures. In particular, for PDS 70, for PDS 70, this is a famous disk where we have a circumprotoplanetary disk. So this is only one of the 2 examples where we have confirmed planet formation in a protoplanetary disk. And finally, we have some summary of the different conclusions of this talk. So we can start explaining what is a dust trap, right? Because this is the main idea of this talk. In a protoplanetary disk, we usually have 2 main components. We have dust grains and we have gas molecules. They are everywhere in a protoplanetary disk, but they have different dynamics because, for example, if we focus on the dust grains only, we have 2 main forces acting on the dust grains. We have the stellar gravitational force and the centrifugal force. Usually they balance each other such that we have Keplerian velocity of the dust around the central star, right? So the dust grain is moving at Keplerian velocities. On the other hand, the gas molecules also have the influence of the stellar gravitational force and the centrifugal force. But in addition, we have pressure gradients because the gas is a gas, right? And we have pressure gradients. The pressure is not constant in the disk, but we have some local pressure gradients. Depending on the direction of the pressure gradient, the disk can rotate sub-Keplerian or super-Keplerian, depending on how the pressure gradient is. So this is important to understand that we have 2 main components in the disk, but the velocities are not the same. So if the velocities are not the same, we have a shear velocity between the dust component and the gas component, right? This shear velocity explains why the dust grains can migrate in the protoplanetary disk, because the mass of dust grains are typically 2 orders of magnitude smaller than the mass of the gas. So the dust is feeling the effects of the shear velocity with the gas, right? So that's the main idea and the physical processes taking place in a protoplanetary disk. So imagine, for example, that we have a dust grain which is moving faster than the local velocity of the gas, right? In that case, the dust grains are trying to move through the gas, So they decelerate because they are losing angular momentum. And when they lose angular momentum, they migrate radially inward because they are just losing energy, right? On the other hand, if for some case the dust grains is moving slower than the gas velocity, then the dust grains are accelerating because they are feeling the effect of the drag of the gas. In that case, the dust grains gain angular momentum and they migrate radially outward, right, to larger orbits of the disk. So this is why we can explain the migration of dust in protoplanetary disk. For example, in a protoplanetary disk, the pressure is not constant, but usually we have a pressure that decreases with radius. Imagine that for some reason we have a perturbation in the pressure at some radius of the disk, like this cartoon, for example. So what happened in this case? In this location, the pressure gradient is radially outwards, so the gas is rotating super Keplerian. And in this location, the pressure gradient is radially inward, so the gas is sub-Keplerian. So the dust grains in this location should migrate radially outward, and in this location, the dust grains will migrate radially inward. So we are trapping dust grains in a specific radius of the disk, right? They cannot escape from this location because the drag forces are trying to push everything in the same location. On the other hand, for example, what do we expect from these models? We expect that, for example, in this radius, we expect a local enhancement of the dust surface density because all the dust is moving to this location. And also we expect an enhancement of the maximum grain size because dust grains are colliding and the probability that they can create larger grain sizes increases. So that's why we expect that the grain sizes in the location of the ring is higher compared with the rest of the disk. From an observational point of view, we also expect that the width of the rings decreases with wavelength if dust trap is efficient. This is because at millimeter wavelengths, we are sensitive to millimeter grain sizes. And we are sensitive to larger grain sizes if the wavelength increases. So if for some reason we can observe that the width of the ring is decreasing with wavelength, this is another test that is telling us that dust trapping is in action in a protoplanetary disk. So in summary, we have drag forces which are pushing the dust grains in the ring of protoplanetary disk. And this is the place where we think that planet formation can be triggered because there is a lot of dust, the collisions between particles is increasing. So we think that maybe planets can form in the rings of protoplanetary disks. So, but there are another mechanisms that are taking place in protoplanetary disks. For example, we know that the dust trap efficiency is proportional to the size of the dust grains. Larger dust grains have a higher effect on the drag forces, so we expect that they are trapped in the location of the ring. But the small grain sizes, they are very coupled to the gas, so they don't have very strong effects on the drag forces. On the other hand, we have diffusion. Diffusion has been shown to be proportional to 1 over the grain size. So the small grain sizes can diffuse everywhere in the disk due to the turbulence of the disk, for example. And we have a competition. We have the drag forces which are trying to push everything in the ring of the disk, and diffusion is trying to merge the dust grains everywhere, right? So we have this competition between these two mechanisms. So as you can see, the small grain sizes are not trapped in the pressure bumps because they are not efficient. The dust trap is not efficient. And also they are also more prone to diffusion. So we expect that those grains are, the small grains are everywhere. So for example, in this cartoon, we have a typical protoplanetary disk with small grain sizes and large grain sizes and the gas. And this is a distribution, a radial distribution of the pressure as a function of radius. And those grains are everywhere. Imagine that for some reason we remove a part of the disk and just let evolve this system. If, for example, after a few mega years or 1 mega year of evolution, we expect a cartoon similar like this one. The small grain sizes should be everywhere because they can escape from the dust trap, and the large grain sizes are expected to be trapped in the location of the dust trap or where the pressure has a maximum, right? So this is the typical cartoon of how the processes are taking place in a protoplanetary disk due to the drag forces of the gas on the dust grains. So this is important because, for example, there are some disks. For example, this is the PDS 70 disk that I mentioned in the first slide, that some people have tried to explain how to explain the presence of the inner disk, because we know that the age of this protoplanetary disk is a few mega years, and there is an inner disk. But if the dust grains are trapped in the main ring of the disk, how can we explain that there is a inner disk? Because we expect that the dust grains in the inner disk are migrating toward the central star, and the inner disk should disappear in a few mega years. For some reason, the dust grains should be feeding the inner disk constantly, right? So in some reason, we should explain how the inner disk can survive. So before continuing with the observations of LkCa 15 and PDS 70, I want to mention very fast how we observe the disk with radio interferometers, for example, like ALMA, BLA, or in the future with the next generation BLA. We have usually several antennas, and these antennas are measuring the brightness of the source that we are observing in the sky. Usually we have an amplitude, which is the amount of energy that the antennas are observing. And we also have a phase, because the antennas are not in the same location. So we expect that the wavefronts that are arriving to the antennas, there is a difference, a geometrical difference or a time difference. So this phase and this amplitude can usually be expressed like an amplitude, a phase, given this complex number. Or we can just write this equation as a real part of an imaginary part of the visibilities. The baselines are important. The baselines are basically the separation between the antennas, right? We usually normalize the separation with the lambda or the wavelength that we are observing. So when the antennas are very far away, we are observing emission from compact emission from the object that we are observing. But if the antennas are very close, we are observing the extended emission of the source that we are observing. So we can trace emission at different spatial scales. That's the main idea of the radio interferometry. Thanks to the Earth rotation, we can trace a lot of baselines. We can just trace the emission coming from different spatial scales from the source that we are observing, and we can coverage the visibility plane in a good way, for example, with ALMA. Here, I only want to highlight that the image that we usually present in the papers, this is only a representation of the data. This is not the robust data that we are measuring with the telescope. This is only a representation, which usually we can compute using the Fourier transform of the visibilities. But the actual data that we measure with interferometers are the visibilities, which this is the robust data. So if we want to analyze and extract the highest angular resolution and sensitivity from the observations, we have to use the visibilities, right? The image is only a first idea how the data looks like. So now we can focus on the different disks that we analyze in this paper. So we are going to start with LkCa 15. What do we know about the dust traps in the LkCa 15? This is a summary of the observations that we have for LkCa 15 at different wavelengths. We have ALMA 9, 7, 6, 3 at different wavelengths, as you can see in the labels. And also we have BLA band Q. This is very long wavelengths. We have, as you can see, we have a ring-like structure in all of them. The resolution is not the same in all of them. For example, in ALMA band 9, you can see that the resolution element is high compared with the rest of the wavelengths. And also for BLA band Q, the resolution is not as good, for example, compared with ALMA band 3, 6, or 7. So as you can see, there are many differences when we observe the same disk at different wavelengths. Yeah? Yes, the resolution here is like 5 AU, more or less. So yes, that's the typical resolution in this particular one. So in the next slides, I will focus on the 3 images with the highest angular resolution. The angular resolution in these are the same. So here I only want to remember that we are observing the dust distribution at different grand sizes, because this is the typical grand size that we can trace at this wavelength, and in the rest of the wavelength, this is the typical grand size. As you can see, we are sensitive to sub-millimeter grand sizes at different wavelengths. That's why we observe differences in the map. For example, you can see that the gap of the disk is deeper in band 3 compared with the rest of the wavelength. Right here, we can see the gap, but it's not as clear, for example, compared with ALMA band 3. So the difference is telling us information about the radial distribution of dust. So this is what I was mentioning before. This is the plot of the visibilities. The idea here is just to focus that we can model the visibilities in order to extract radial profiles of the disk. For example, we have the visibilities in ALMA band 3, band 7, and band 6, which is given by the colors. And the model that we create to reproduce the data is given by these black solid lines in each panel. So the details are not important here, but the important thing is to see that we can extract the intensity radial profiles of the disk or the brightness temperature, right? So the idea is the same. So as you can see, we can see the three main ring structures. The inner one is very difficult to observe from the image plane, but from the visibilities, we can observe it. In the inset panel, you can see again the three panels, but we normalize the intensities to the peak of the emission. So as you can see, the main idea in this plot is to see that the longer the wavelength, the narrower the ring, right? You can see this initial idea or initial guess that dust trap is taking place in LkCa because there are very narrow rings at longer wavelengths. So this is the first hint of dust trap in LkCa. So here we have the radial profiles again at the same wavelengths that I showed in the previous slide, at band 7, 6, and 3, and the corresponding wavelengths. So as you can see, the main ring has a narrower distribution compared with the longer wavelengths. But we can try to measure this, the width of the rings. For example, we can use Gaussian functions just to reproduce the full radial profiles. The different Gaussian functions that you can see here is a combination that is able to reproduce the data in all the cases. So in this way, we can measure the width of the ring at each wavelength and at each radius. So yeah, this is the extended emission because we have three rings, but we also have extended emission. So we have to use a wide Gaussian to reproduce the extended emission. So if we focus, for example, in the ring at 69 astronomical units, which is given by the crosses here, you can see that if we measure the full width half maximum, this full width half maxima increases with frequency, as you can see here. And the same for the ring at 42 astronomical units or 101 astronomical units. So this is another test that is telling us that, yes, the width of the ring is increasing with frequency. So a dust trap is probably one of the explanations of this particular morphology of the disk. But we also have to test another ideas, right? So for example, in LkCa, we have at each radius the spectral energy distribution. We know what is the intensity of the disk at different frequencies. For example, we have this spectrum, for example, intensities versus frequencies. So we try to model the spectrum by a best fit model that is able to reproduce the data simultaneously, using a solution of the radiative transfer equation, right? Probably the students have seen this solution in the radiative transfer class. This is the typical solution for the radiative transfer equation. However, we also include an analytical solution using scattering in the disk, which is also important. We did a full analysis of the scattering influence on the intensities that you observe in disks. So we are analyzing, we are including additional terms, right? All the tools to fit the spectral energy distribution given this large solution is available in my GitHub. So you can use the tools in this to fit the data. But the main idea here is that we can, for example, use the temperature, the dust surface density, and the grand size. And these three parameters are enough to reproduce the intensities in this equation at different wavelengths. So we can use these three parameters to infer the spectrum and just try to look at best fit of the spectrum. So we can do this at every radius of the disk. We can do everything the same simultaneously, and we can best a best fit or the radial profile for the dust temperature, for the dust surface density, and for the ground size. So that's the methodology that we are using. And these are the results. This is the results for the dust temperature, radial profile, dust surface density, and ground size. So there are several important properties in these plots, but let's focus on these ones. As you can see, in the position of the rings, we are observing high densities of dust, right, in this location. And also, in the location of the rings at 69 and 101 astronomical units, there are high ground sizes, right? So this is another evidence using the spectrum of the disk that is telling us that a dust trap is acting on LkCa 15, right? We have a lot of dust and high ground sizes in the location of the rings of LkCa 15. Okay, just to test another ideas, we also use models to reproduce the characteristics of LkCa 15. And in particular, we use dust pi simulations. This is a script which is available online, where you can, for example, just simulate how the dust grains are moving in the protoplanetary disk when you have some gas distribution. So we evolved the disk for 1 mega year, for example, which is the age of this protoplanetary disk. And we are changing, or we are testing different models. The different models that we are testing is one where we change the alpha parameter, which is controlling the turbulence or the diffusion of the disk. Typically, this value is between 10 to the minus 5 to 10 to the minus 3. So in the different models that we are testing, we are changing the alpha parameter. Also, we are changing the fragmentation velocity. What is the fragmentation velocity? This is the velocity where the dust grains collide, and instead of just stick together and create a larger grain size, they collide and they fragment each other. So they are creating smaller grain sizes when they collide. Typically, this fragmentation velocity is between 1 meter per second or 10 meters per second. So we are testing different scenarios just to check what is the best model that is able to reproduce the data. So for each model, this is a plot where we have the density or at different radius of the disk and for different ground sizes. So we are observing the densities of all the different population of dust in the disk. And we can create the expected millimeter maps of these simulations. After comparing the maps of the simulations with the data, we observe or we conclude that the best fit or the best model that is able to reproduce the data is the one where the alpha parameter is 10 to the minus 3 and the fragmentation velocity is like 10 meters per second. For reference, this is how the images looks like at the different ALMA bands. So they are very close to the observed images that we observe with ALMA, for example. So we have a very good match. So we can put constraints on the turbulence of the disk and also on the fragmentation of velocity of dust. On the other hand, just as an additional result of this paper, is that we observe a point source in the center of the disk. For example, in ALMA band 7, you can see that it's very difficult to observe a point source in the center of the disk. Also, it's the same for ALMA band 6. However, in band 3, there is a point source. There is also some evidence that there is a point source in the BLA band Q. It's more complicated, but there is some constraints on the point source. And after analyzing the data, we conclude that the point source is not only dust continuum emission, but there is also free emission. We have ionized gas, which is contributing to the emission in the center of the disk. Probably we have, from this plot, we can see that an image says more than 1,000 words. However, a spectrum says more than 1,000 of images. And you can see here the spectrum of the disk. For example, if we focus on the full emission of the disk, the total flux of the emission, this is the spectrum. You can see that the typical slopes that we observe, this is the spectral index. The typical slopes are between 1.8 and 3.5, for example. And these slopes are expected if the emission is coming from dust thermal emission. So the full emission from the disk is mainly dust, right? But if we create the spectrum analyzing only the flux in the inner compact emission, you can see that the slope that we observe is between 0 and 0.3, and these slopes are consistent with free emission, right? So we know that the emission coming from the compact inner disk is not only dust, but there is an important contribution from free. So yeah. Okay, now we can continue with PDS 70. This is the other disk that we analyzed last year. I will go faster for PDS 70 because most of the methodologies that we use in PDS 70 are similar to the ones that we use for LkCa 15. So we can, you already know the methodologies that we are using. So these are the maps that we have for PDS 70. Again, we have multi-wavelength observations of the same disk. You can see the famous map is the one at ALMA band 3 or 350 gigahertz. We have a ring-like structure in all the cases, but there are differences. For example, in ALMA band 3 at 100 gigahertz, you can see that there is a crescent, which is very important compared with the rest of the emission in the ring. But here the crescent is not as, the contrast between the crescent and the ring is not as high, for example, with this observation. So the different wavelengths are telling us information about the dust distribution in the disk. Right? The new observation in this particular paper is the ALMA band 9. This is the 671 gigahertz, which is using to complement all the observations. So the idea is very similar. We analyze the visibilities of the data. This is only a reference to show that we are using the visibilities. This is the real part of the visibilities versus the baselines, just to check that we are creating a model to extract the intensity radial profiles. So you can just ignore this slide and just focus on the intensity radial profiles, right? The emission versus the radius. So these are the observations that we have at the different wavelengths, depending on the color. You can see that we have a ring-like morphology in all the cases, but there is something particularly different for the 0.4 millimeter observations. You can see that the peak of the ring is not located at the same location compared with the longest wavelength. For example, there is an important shift, right, of the position of the ring. Maybe we can focus on this region around the position of the ring. You can see the shift very clear. For example, for the longest wavelength, you can see that all the position of the ring is, all of them are located in the same place. However, for the purple line, you can see this offset. The offset is like 0.1 arc-second or something like that. We are sensitive to this shift. So the smaller the wavelength, we are observing important shift of the peak. For reference, we also include the normalized infrared observation. This is even a shorter wavelengths of the PDS 70. You can see that at infrared, the peak of the ring is even has moved to the inner region of PDS 70. So there is an important trend in these particular properties of the emission, right? So how can we explain this particular property? For example, you can see here the peak shift, for example, at the different wavelengths. And I want to remark again that at different wavelengths, we are sensitive to different grand sizes, right? In particular, if we know the wavelength, we can use only this equation to estimate what is the grand size where we are sensitive, right? So in particular, the 0.4 millimeter wavelength is sensitive to small grain sizes, and the rest of wavelengths are sensitive to large grain sizes, right? That's the idea that we want to test to reproduce these particular properties of PDS 70. Before continuing, I just want to mention that there is another important property of the 0.4 millimeter observations. This is the outer shoulder. For example, you can see that we observe a shoulder in this location, and this shoulder is not observed in the rest of the wavelength. So what is the origin of this shoulder, right? How can we explain the presence of this shoulder? There have been several previous studies who tried to explain how a shoulder can be created in the emission of a protoplanetary disk. The idea is very simple. If you have a protoplanetary disk and you input a planet in the protoplanetary disk, this planet interacts with the gas, and this gas is driven radially outward of the planet. In that case, the gas is moving radially outward, and remember that the small grain sizes are coupled to the gas. So the small grain sizes will move together with the gas, right? So if we focus, for example, from the distribution of some hundreds of micrometer dust, we observe a distribution that can be that you can see in orange in this plot. But if we focus on centimeter grain sizes, the distribution is given by the green area. So in total, if you consider the contribution from small grain sizes and large grain sizes, you will observe something like this one, which is, it looks like a shoulder, right? So in the cases where you have a planet, you expect to observe shoulders in the distribution of the disk. And this is again telling us that we are tracing small grain sizes from the 0.1 millimeter observations, and from the large observation, from the longest wavelengths, we are observing the distribution of large dust particles, right? So this is again helping us to understand the properties of dust, or the distribution of properties in PDS 70. So again, we test the fit to the spectral energy distribution of PDS 70. These are the main results. The different colors are different models that the referee asked us to test in this particular fit. But the main idea is that in the position of the ring, we are observing high densities in all the models, or different models. And also we are observing a peak of the grain size. So we have very large grain sizes in the ring. In the cavity of the disk in particular, the best fit is telling us that this is compatible, for example, with centimeter grain sizes, millimeter grain sizes, or even is compatible with very small grain sizes, down to 10 micrometers, for example. So in the gap, we can have particles, very small grain particles, right? So the best fit is telling us this important information about the distribution of dust in the gap. Just to test a possible theoretical scenario that is able to explain how the peak moves with radius at different wavelengths, we test some dust segregation models where the dust is just moving thanks to the pressure gradients in the disks. And we have 3 different models. The only difference is that we are changing the alpha parameter, which is controlling the turbulence or the diffusion of the disk. And for example, we have the dust surface density as a function of radius for different grain sizes, right? For example, from 1 micrometer to 10 micrometers, or depending on the color, for different grain sizes. So we are changing only the alpha parameter. For example, if we focus on this very low turbulent disk, you can see it that all the grain sizes concentrate in a ring, right? So we have all those grains in this location. If we increase the turbulence to 10 times to the -3, you can see that in that case, the turbulence is high enough to remove all the dust grains from the ring, and they migrate radially inward of the disk. So this cannot explain the presence of the ring in the map. However, if we are in an intermediate case, for example, 2.5 10 to the -3, only the large grain sizes are concentrated in the position of the ring, but the small grain sizes move radially inward because the diffusion is important for these small grain sizes, and they can escape from the ring structure. So this is the best model that is able to reproduce the different observations at different wavelengths of PDS 70. So, for example, this is a cartoon of how the properties of PDS 70 looks like. This is the same slide that I show at the beginning of this talk. But in particular, for PDS 70, we think that the large grain sizes are concentrated in the ring of PDS 70, and by large grain sizes, we are using millimeter or centimeter grain sizes. And in the gap, we have very small grain sizes, right? So this is the picture that we have of PDS 70. So the small grain sizes are just moving radially inward, and they are escaping from the dust trap. This is important because this also can explain another mechanisms that are taking place in PDS 70. For example, we know that the small grain sizes are just escaping from the ring, and they are moving toward the inner disk. They are constantly feeding the inner disk, and they can explain how the inner disk can survive, because there is a lot of mass which is constantly moving toward the inner disk. But also, we know that the small grain sizes, when they are in the outer disk, they have ices in the surface of the dust. So this ice is frozen, but when the dust grains are moving radially inward, they cross some specific radius, which we call the snow line, when the temperature is high enough to sublimate the ice in the surface of the dust. So after they cross the snow line, we expect that the water is, we have gas molecules, for example. So in this location, we should detect water in the inner region of PDS 70. And for example, there are observations from 2023 using the James Webb telescope, which have observed that there are water lines in the inner region of PDS 70. So our model is also able to explain how the water is transported from the outer regions of the disk toward the inner regions of PDS 70. So this is my last slide. So in particular, we test and we found how the dust traps are taking place in the disk around LkCa 15 and PDS 17, and this is the main mechanism shaping the dust continuum morphology in both disks. Also, from the dust trap in LkCa 15, we found that the dust grains are trapped in the ring-like structures of LkCa 15, and the best model for the turbulence parameter that is able to reproduce the data is like in the order of 10 to the minus 3. For PDS 70, on the other side, we have large grain sizes, millimeter or centimeter grain sizes, which are trapped in the main ring of PDS 70. However, the small grain sizes of tens of micrometers or smaller, they filter toward the inner disk, and they are constantly feeding the inner region of PDS 70. And the best model for PDS 70 that is able to reproduce the data in our case is a bit higher than in the previous case, like 2.5, 10 to the minus 3. So that's it, and thank you very much.
Thank you, Aníbal. We have enough time for questions.
Gracias. Felicitaciones, Aníbal. Should I speak in English or Spanish? What do you prefer? Felicitaciones, es un mecanismo muy interesante de atrapamiento. Y tengo una pregunta pues bastante inocente. El papel de la radiación no ha sido considerado, por lo menos en lo que has dicho, no sé si lo has pensado, pero la presión de radiación que actúa sobre los granos de polvo, no sé, en algunos casos y en algunas zonas podría ser importante. Y por otro lado, el efecto Poynting-Robinson, pues estaría imprimiendo una torca en algunas de las de los granos. No sé si has considerado estos efectos.
Sí, sí me escucho ahora. Sí, de la primera, sorry, I will switch to English. So in the first case, for example, the temperature from the central star or the pressure from the central star is only important in the most inner compact region of the disk. Because the drag forces, if we compare the drag forces with the pressure from the radiation, is much larger than the pressure from the star, for example, the radiation from the star. So we can neglect the pressure from the central star in these cases. In the outer region, the drag forces are more important, right?
But infrared pressure might be important.
Yes, of course. For infrared, it's more important, right? But here we are only analyzing millimeter grain sizes at millimeter wavelengths. So in this regime, this is not important, right? So, and for the second question, that is important in particular for polarized observations of the disk, right? when you have these effects where the dust grains are just aligned with the, for example, with the radiation of the central star or the magnetic fields, you should observe some specific pattern of the polarization observation, right? So we are not including here polarization observation because it's very difficult to observe polarized observations with ALMA, for example, because the polarized fraction is very low. So you need a lot of time to observe this kind of observations. So there are only like 2 or 3 examples where the polarized images have been observed with ALMA. So in that case, we should, maybe in the future, we can improve it, right? But yeah.
Yeah, but the point in Robertson does not need a magnetic field. Yeah, it acts just like a torque, absorbing when those grains absorb infrared radiation.
Yeah, of course, yeah.
Yeah, but so I didn't understand why polarization might be important.
Yes, because if you have aligned grains, for example, if you have all the grains aligned with, for example, some torque, like the one that you are mentioning, you should expect a polarization pattern in the maps of the polarized observation, right? So that's the important message that I try to say, yeah.
No, but the torque is angular momentum transport, not torque to align those grains.
Okay. Okay, in that case, I don't know, we have neglected that effect in the past, but should be interesting to just to double check the order of magnitude of this torque compared with the drag force, for example, right? So yeah, thank you.
Leonardo?
No se escucha.
Hola. Perdón, es que no tengo casi voz. Voy a tratar de gritar, perdón, es que mi voz todavía no. ¿Diste la definición del parámetro alfa al principio de tu plática?
No.
Me perdí un poco porque es el parámetro de turbulencia.
Sí.
Y es, yo creo que un parámetro importante. Yo no sé mucho del tema y de turbulencia, sé la turbulencia Kolmogorov, pero en fin. Nada más brevemente.
Es una parametrización que se ha utilizado desde los 70s, que es la Shakuran-Shunyaev parametrization para poder determinar cómo es la turbulencia. Y todo lo que no sabemos de la turbulencia se lo echamos la culpa al alfa parameter, ¿no? Es como, es una parametrización, pero al fin y al cabo tenemos un factor ahí.
Sakura-Shunyaev.
Sí, exacto.
¿Y Kolmogorov no es?
No, eso no lo hemos introducido. Usualmente hemos utilizado Shakuran-Shunyaev.
Gracias.
Es que usas el alfa para la turbulencia y también para el índice espectral y luego para el tamaño de los granos y todo. Y entonces,
sí, usamos, sí, exacto, usamos alfa para el índice espectral y para parametrizar la turbulencia. Ahí hay algo que deberíamos cambiar. Bueno, al índice espectral usualmente le ponemos subíndices de entre qué frecuencia y eso ya nos da una idea, ¿no? Pero puede ser confuso, claro, por supuesto. Pero todo el mundo lo hace igual.
Tenemos 2 preguntas en Zoom. Karina, por favor, abre tu micrófono y haz tu pregunta.
Sí, thank you, Aníbal, for your very nice talk. My question was about the first case, so LkCa 15, and my question was if optical depth effects, because you're using different wavelength observations, so if optical depth effects can affect your results from the width of the rings, which are decreasing with wavelengths, which are evidence of this dust trap that you were mentioning. But I was wondering if optical depth effects or even scattering can affect these results.
Yeah. Yes, you're right. For example, we take into account the optical depth when we model the spectral energy distribution. So the optical depth is taken into account. For example, in the previous case where we only analyze the width of the ring, you can see that we can say that maybe there is a dust trap in the inner 42 astronomical unit ring, right? And also in the rest. But from fitting the spectral energy distribution where the optical depth is taken into account, we finally found that the ring at 42 astronomical unit, there is not a local enhancement of the dorsal phase density in that range, right? So the responsible of the increase of the width with the frequency in the inner ring is the optical depth actually, right? It's not a dust trap. So we are saying that there is only a dust trap in the ring at 69 and 101 astronomical units. In this case, we can confirm that the increase of the full width maxima is not an optical depth effect, but there is also a dust drop, right? So yes, that's why we have to test the different scenarios. We can not only use the width of the ring measured from the radial profile, but also you can take into account the optical depth. And this is what we did in the second methodology, right? Just to confirm. Yeah.
Yeah, because I remember from your models, from this methodology, that you also obtain optical depth, right?
Yes.
So what about the optical depth around the rings that you mentioned?
Yes, I didn't show the optical depth results in this presentation, but the inner one is close to the optically thick regime. So that's why we observe the increase of the width with frequency. But these rings are close to the optically thin regime, so they are thinner than the inner one. So that's why we can observe the contribution of dust or the effects of dust at different grain sizes, right? But you're right, only the inner one is optically thicker than the outer ones.
Okay, thank you. No, and my last question was actually about this slide over here. So because of the inner ring is optically thick, then that is why you have like a very high dust size, maximum dust grain sizes there?
Yes, you're right, because we are in the optically thick regime. It's very difficult to put constraints on the maximum grain size because the problem is degenerated. So in that case, you can see that the maximum grain size is increasing toward the inner region of the disk. Don't believe the innermost compact region because we have free contamination. But from here, the dust grain is just increasing toward the inner disk, right? And here we are not sensitive to the grain sizes in the midplane because we are in the optically thick regime. So that's the answer, the main conclusion that we are doing from this particular ring.
Thank you.
Yeah.
Okay, thank you. And now also in Zoom, Mauricio Reyes, please go ahead.
Hola Aníbal, muchas gracias por la presentación. Te comento que lamentablemente donde estás apuntando el láser no se ve para los que estamos en Zoom. Nada más quería comentarte, obviamente en el trabajo pues utilizas algunos códigos que probablemente son de lo más avanzado que tenemos ahorita, pero no dejan de tener una serie de simplificaciones. Caso de DustPy, por ejemplo, pues es un tratamiento unidimensional, no toma en cuenta todos los factores que tienen que ver con asentamiento, etcétera, ¿no? Sí. Mi pregunta es, ¿qué es lo que más te preocupa de las suposiciones que hiciste para llegar a este resultado? Yo, por ejemplo, me llamó la atención la presencia o la necesidad de la presencia de un planeta de una masa de Júpiter en 50 unidades astronómicas, ¿sí? Que entiendo que hay algunos casos observados, pero pues no es así como muy común, ¿no? O no sé si hay alguna otra manera de formar este pressure bump, ¿no? Entonces, no sé si pudieras platicarnos un poquito así como que qué es lo que consideras que son los caveats de tu trabajo y qué cosas interesantes se pudieran hacer por ahí, ¿no?
Sí, desde luego. Digamos, las simulaciones son bastante simples en el sentido que son unidimensional. No estamos tomando estructuras en el plano 2D del disco, mucho menos tridimensional como arriba del plano medio del disco. Obviamente, meter más física implica más trabajo de cómputo, por ejemplo, para todos esos trabajos. Decidimos hacerlo 1D, por ejemplo, porque la mayor parte de la morfología que vemos de los discos realmente es axisimétrica. Realmente no estamos viendo algo como que tenga importantes asimetrías azimutales, por ejemplo. De tal manera que no es necesario meter el 2D en estos casos en particular, ¿no? O sea, a lo mejor no... Podrían haber pequeñas diferencias, pero no va a cambiar significativamente. Verticalmente, como nosotros estamos trazando granos que son milimétricos o submilimétricos, esperamos que estos granos están cerca del plano medio, ¿no? Entonces no somos sensitivos, por ejemplo, a los granos que están en la superficie del disco, porque a estas longitudes de onda no somos sensibles a esos granos. De tal manera que la parte vertical también podemos suponer que, digamos, no somos sensitivos, por lo tanto, aquí todo lo que estamos viendo es en el plano medio del disco, ¿no? Entonces, esas son unas de las justificaciones por lo cual una simulación 1D, en nuestro caso, funciona relativamente bien, ¿no? Obviamente, uno puede meter cuanta más física sea posible en las simulaciones y esto podría ir cambiando un poco la perspectiva, pero creo que en este es una buena aproximación al problema real, ¿no? El problema 3D, por ejemplo. Sobre lo del 50 masas de Júpiter, no entendí muy bien eso. ¿Por qué decías que necesitábamos un planeta de 50 masas de Júpiter?
No, porque decía para hacer un gap a 50 unidades astronómicas.
Ok. Sí, ok. Sí, por ejemplo, aquí no estamos, para el LkCa no estamos diciendo que el origen de los anillos sea un planeta. Realmente estamos caracterizando cómo es la morfología del disco, pero no sabemos qué es lo que está creando en particular el pressure bump. Una de las posibles explicaciones es obviamente un planeta que podría estar creando los gaps que estamos observando. Pero hay otras alternativas. Por ejemplo, hay unas cosas que se llaman pressure jumps, que simplemente es que cuando los granos de polvo atraviesan ciertas snowlines de ciertas moléculas, por ejemplo, simplemente las propiedades de los granos de polvo van a cambiar. Por ejemplo, el hielo es el ejemplo más directo, creo yo. Porque cuando los granos de polvo tienen hielo en la superficie, por ejemplo, es más fácil que se peguen si tienen estos mantos de hielo, ¿no? Cualquiera ha visto esta típica figura de que alguien pone la lengua en un poste congelado y se le queda pegado, ¿no? Lo mismo queremos que está pasando con los granos de polvo. Sin embargo, cuando cruzan la snowline y el hielo se derrite, básicamente, simplemente las propiedades de pegamento, digamos, del polvo cambian. Entonces, eso lo que crea es que los granos se empiezan a acumular en ciertos radios muy específicos y pueden crear también subestructuras. Entonces, esa es otra alternativa para explicarlo, ¿no? De esa manera podemos dar diferentes orígenes a las estructuras, pero en particular en este paper no estamos apuntando a ninguna de ellas porque de las observaciones que tenemos no tenemos ninguna evidencia extra que nos esté sugiriendo que es un planeta o es otro mecanismo, por ejemplo. Para eso necesitaríamos observaciones de gas, por ejemplo, analizar el gas, que de hecho hay gente que lo ha analizado en estos discos en particular y ha sugerido que quizás hay algunas perturbaciones en el gas que podrían ser sugeridas por un planeta, pero no es muy claro, ¿no? Entonces, hasta el momento no es muy claro cuál es el origen de las estructuras que estamos observando.
Bien, ¿más preguntas? Sí.
Bueno, respecto a esto, tal vez pudieran ser estas inestabilidades térmicas, claro, tipo Vishniak, que hace que, bueno, si está corrugada la cosa, haya lugares donde se acumulen y otros donde falten, ¿no? No sé.
Sí, hay gente que también ha echado la culpa a las subestructuras a inestabilidades térmicas, por ejemplo, sobre todo si somos sensitivos a la temperatura del disco, a longitudes de onda cortas. Entonces, lo que estamos viendo del mapa del disco realmente son perturbaciones en temperatura y no en densidad, que es lo que uno podría pensar, ¿no? Entonces, estas inestabilidades térmicas también pueden crear estructuras que finalmente las observamos como anillos. En inestabilidades gravitacionales, por ejemplo, hay gente que ha también supuesto que si tenemos un anillo que se está volviendo muy denso, eso podría empezar a ser gravitacionalmente inestable y podría empezar a crear estructuras compactas, básicamente, ¿no? Entonces, sí, hay diferentes mecanismos que podrían explicarlo, ¿no?
¿Alguna otra pregunta aquí en el auditorio? Parece ser que en Zoom ya no hay más preguntas tampoco, entonces pues le agradecemos a Aníbal. Y nos vemos la siguiente semana para el siguiente coloquio.